Hello everyone, Mr. Rodriguez here with another video for you guys. Today we are going to be talking about Lesson 9, the scaling principle for volume. So our objective for this lesson is students understand that given similar solids, a solid is really just a 3D shape. So given similar solids, A and B, so that the ratio of their lengths is A to B, then the ratio of their volumes is A cubed to B cubed. So just to unpack that a little bit, it's saying if you have two similar solids, two similar 3D shapes, and if you have the ratio of their lengths, AB, some number A, and some number B, then the ratio of their volumes will be A to the third power, or A cubed, to B cubed. But I think that'll be a bit more clear once we get into the lesson itself. So let's take a look at our little opening exercise here. So it says for each pair of similar figures, so you have two similar shapes, write the ratio of side lengths, AB or CD, that compares one pair of corresponding sides. Then complete the third column, so this column over here, by writing the ratio that compares the areas of the similar figures, and simplify the ratios when possible. So let's take a look at kind of number one over here. So we have two right triangles, and we're told that they're similar. That's what this little kind of thing means over here. It's saying triangle A is similar to triangle B. And first they want us to write the ratio of side lengths. So we see this kind of 3 over here corresponds to the 2 down there, right? And the 6 corresponds to the 4, right? So the two smallest sides correspond to each other, and the two larger sides here correspond to each other as well. So we have, right, 3 goes to 2, and 6 goes to 4. So we can really just work with one of the side ratios here, right? Because it says ratio of side lengths AB or CD. So we could just work with one of them. If we take 6, 4, so 6 to 4 is one ratio. Notice if we simplify that, if we divide both sides by 2 here, so divide by 2, that becomes 3, 2. So our ratio of sides is 3 to 2. So it's the same one that was up here because this one was actually already in its simplest form. So it's going to be the same ratio, right? That was the idea of similar shapes, is that, you know, if you have kind of this number here and this one down here, you say multiply both numbers to get the new ones over here. So 3 to 2 is our answer over here. That's the ratio of sides. So it's a 3 to 2 ratio, right? And now let's look at what the ratio of the areas of the two shapes will be. So the first thing we have to do is get the area of this triangle and of this one. So maybe let's do that kind of over here. So let's do area of triangle number 1, the bigger one. Remember, the area formula for a triangle is area equals 1/2 base times height. So for this bigger triangle, our area would be 1/2. Our base is 3. And our height is 6. So our area here You could put that in the calculator or you can do it in your head, but our area would end up being 9 for the bigger triangle. And then for the smaller one, we have, again, same formula. So area equals 1/2, and then times base times height. But our base here is 2, and our height is 4. So again, if you calculate this out, we'll get that our area is 4. So then these are our two areas, right? This one here, up top, and then the area down here. So 9 and 4. So if we go back over here, we have our area ratio is 9 to 4. And then it asks us to simplify this more. And one way we can kind of simplify it is if we change this to 9 is the same thing as 3 squared, right? And 4 is the same thing as 2 squared. And really, I shouldn't necessarily say that's a simplification. That's more of kind of just a different way of writing it. And the reason I write it like this is because I want to highlight, notice the ratio of sides was 3 to 2, and then the ratio of areas is 3 squared to 2 squared. So do you see the steps here? First thing we did was we got the ratio of side lengths. We simplified it to their simplest form. We calculated the area for each shape here. We wrote out the ratio of the areas, in this case 9 to 4. And then we put it in this sort of new form over here, 3 squared to 2 squared, to emphasize basically that it's just almost like the same ratio as over here, but just squared. So those are basically the notes for this first part. For your classwork now, I want you to work on this problem here with the two rectangles. So this one here, 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 and here. And again, you'll find it's a similar kind of method as the one we did up here, right? So you just have to find and know the area formulas for these different shapes, right? So let's look at some of these questions, these kind of conceptual questions in part B over here. The first one says, state the relationship between the ratio of sides AB and the ratios of the areas. So again, if we look up here, what I emphasized, right, is that the ratio of the side lengths, right, you could say this is A to B, and then the ratio of areas ends up being whatever the ratio for the side lengths was over here, and we just square it over here, right? So if we come back to this question, so really if the ratio of sides is A to B, then ratio of areas, so this is for sides, ratio for areas will be A squared to B squared. So whatever number A is, you square it over here, and whatever number B is, you square it over here. Now it asks us to make a conjecture or an educated guess as, or maybe a theory, I should say, as to how the ratio of sides AB will be related to the ratio of volumes, right? That was our real objective, to talk about volume. This kind of exercise with area was kind of just like a little practice to get you to kind of see what it's like for 2D shapes. And now we're going to see what it's like for 3D shapes. So if you kind of think about it, remember area of 2D shapes is in 2 dimensions, right? That's why, just like up here, it's squared, right? Because it's 2 dimensions. But volume is in 3 dimensions, right? 3D shapes. Because remember, if you have a 2D shape, like, again, like a square, it's just 2 directions, right? Kind of left, right, and up, down. But if you have a 3D shape, like, say, a cube, something, if you could kind of imagine this being 3D, then you have both this kind of, forward, left, right kind of direction this way. And then you also have height, right? You have how tall it is. So you have 3 different directions, or it's 3-dimensional. So if you kind of think about it, again, if we have our ratio of sides, A to B, again, this is for 2 kind of similar shapes. So if you imagine if you had 2 similar cubes, you could take one side of the smaller cube, say, and call it A, take a side of the bigger cube and call it B, and you would have this ratio here. And then the question is asking us to think about what would the ratio for volumes be. And again, this is sides. And then volume would be a cubed, or a to the third, to b cubed. So if we have it for 2D shapes, it's squared. If it's for 3D shapes, if it's for volume, right, it's cubed, or to the third power. Because there are 3 sides, right? Or I should say 3 sides going in different directions. So let's take a look at an example using this new idea here. Oh, first we have a little C down here. What does it mean for 2 solids in 3-dimensional space to be similar? Well, it's really just the same idea as for 2D shapes, right? If you remember similarity when we're talking about, say, 2 2D shapes, like a small triangle and a big one, the idea with this is just that they might be different sizes, but they have the same general kind of shape. So for 3D, it would be the same idea. You would have 2 3D shapes that basically look the same, but one of them would be bigger than the other, right? Okay, and now we're ready for our example with volume. So it says each pair of solids shown below is similar. So if we look at this kind of first example over here, we have these 2 cones, right? And they're similar. So they're the same shape, but different sizes. And just like in the sort of part 1 we did up there, it asks us to write the ratio of side lengths, AB, comparing one pair of corresponding sides. Then complete the third column over here by writing the ratio that compares the volumes of the similar figures. And it asks us to simplify ratios when possible. So let's take a look at side lengths. So again, we already know they're similar. So it doesn't matter which kind of side length we choose. We could choose to work with the height here, or we could choose to work with the radius down here. Whatever we want, as long as we're taking corresponding measures. So let's say we work with the radius down here. So we have the radius of the base, right? And that is 5 to 4. Now notice here, there's not any way we could simplify this, right? They have no common factors. I can't divide both sides by, say, 2 and keep the numbers whole. So we would say this is the simplest form here. It's 5 to 4. And again, just to clarify, if you use 10 and 8 instead, you could write that out. And notice this time you can simplify, you could divide both by 2, and you would get 5 to 4, which is the same. So again, just to emphasize my point that as long as you're choosing corresponding sides, it doesn't matter which ones you choose. So now let's look at ratio of volumes. Remember before, we just had to get the area of each shape. But now, since we're dealing with volume, we have to get the volume of each shape. So if you remember from a previous lesson, the volume formula for a right cylinder is we have volume equals 1/3 pi r squared times height. So again, it was basically just the area times height, and then since it's a cone, it's 1/3 of that. So let's say we're looking at volume of, let's maybe call this 1, and this is shape 2, so the smaller one is 2. So let's say we're looking at the volume of solid number 1 here, cone number 1. So let's say we have V1 equals 1/3 pi, and now we want radius. So the radius of this larger cone here was 5, right? So then we would have times 5 squared times height. And height, again, if we look, was 10, right? So times 10. And if you do this, if you solve this, right, and simplify, you'll get that volume 1 equals, let's see, so 5 squared is 25 times 10. That would get you 250. And then times pi, let's keep pi in here. And then since it's times 1/3, we could just put all of that over 3. So that's kind of how we could write the volume for 1, shape 1 clearly. And now let's look at shape 2 over here, figure B. So let's say we have V2 equals, again, it's the same formula, but this time, instead of 5, right, our radius here is 4, right? So 4 squared. And then times, this time the height is 8. So then our final answer here is, again, it's all multiplication. As long as we do it in the parentheses first, it doesn't matter afterwards which order you multiply things in. So we have 4 squared is 16. 16 times 8 is 128. So we have 128 times pi, right? And similarly up here, times 1/3 is the same thing as divided by 3. So this is our volume 2. So if you set up the ratios, you'd have volume 1 is 250 pi over 3 to 128 pi over 3. And now when you're doing a ratio, right, you need to compare kind of what's different in a way, right? So if you imagine you can simplify this more, if you were to, if you multiply both sides by 3, you can get rid of the 3's at the bottom, right? So that would then become, it would just be 250 pi to 128 pi. Notice if we, since there's pi on both sides, if you divide both sides by pi, you can get rid of the pi's. And lastly here, you'll notice you can also simplify this further if you divide both sides by 2, right? 2 is a common factor. Then you would get 125 to 64. And now, again, we want to get it kind of just like when we had up here, and we wanted to get it into this this sort of form with the squared. Now we want to get this into a form with something cubed, right? Because that's what we said that volume would be, right? Like a cubed to b cubed. So we have to kind of think about it here. What cubed equals 125, and what cubed equals 64. There are different ways you could figure this out. If you do have a calculator, there is a cube root button you can use. But one thing that might be easier is I am going to post, at least for my class, a kind of document that has different numbers and their cubes, and numbers and their cube roots. So you can check out that document to find the answer here, or you can Google it. But anyway, you want to figure it out. If you have 125, the cube root of that would be 5. So then that means that 5 cubed, 5 to the third power, is the same thing as 125. And again, over here, we have 128. We have 64 over here. So the cubed root of that is 4. So that means 4 cubed is the same thing as 64. And, you can put this in your calculator, 4 to the third power, to check it out, right? 5 to the third power is 25. So then we've written it now in the form that they want. So again, notice we have that same relationship. Remember, our answer over here was 5 to 4. And I know it's a little small, but our answer down here is the same thing, but with cubes, right? 5 cubed, 5 cubed, and 4 cubed, right? So you see we have that same relationship. So now we've done an example of similar areas up here, similar shapes of areas, right? And I wanted you to do these 4 problems for classwork. And then down here, we did this volume example up here. And then you could work on these problems down here as classwork. Just pay attention that there are going to be different volume formulas for each shape, right? So this shape up here was a a cone. This is a rectangular prism here, so a triangular prism. So just make sure you're using the right volume formulas for the different solids. All right, good luck. Please feel free to reach out to your teachers if you need any help with this. Please check out the live tutoring that Digital Harbor offers from 1 to 3 on Blackboard Collaborate. We want to be there for you as much as possible. I know this can be kind of complicated stuff, so please do reach out to us. We're happy to hear from you. We want to help in any way we can. All right, good luck and enjoy the week.